Empty space is not empty. What appears as a void is a roiling, perpetual storm of creation and annihilation. Virtual particles flickering into and out of existence, each obeying the strange rules of quantum field theory. This fabric of nothing is saturated with energy, an uncountable sum of microscopic fluctuations known as zero-point energy. But this energy, though fundamental, remains untouchable. It doesn't heat objects, it doesn't push against walls, it cannot be harvested, only inferred through its indirect influence on phenomena like the Casimir effect. The problem is not its invisibility, the problem is its scale. Theoretical estimates of vacuum energy diverge to the absurd, exceeding observed values by 120 orders of magnitude, the largest discrepancy between theory and experiment in the history of science. This is not a rounding error, this is a foundational wound. Something is catastrophically wrong in how physics describes the empty stage upon which all matter dances. Attempts to subtract, cancel, or renormalize this infinite quantity only mask the wound without healing it. The vacuum is not a passive backdrop. It defines what is possible in space-time. Yet we cannot understand it, control it, or reconcile its magnitude with the expansion of the cosmos. What we call nothing contains too much of everything, and that contradiction, vibrating at the very root of our models, will not be fixed with better math. It is a philosophical fracture disguised as a physical one, the irreversibility of time. The laws of physics are indifferent to direction. Whether a particle moves forward or backward in time, the equations remain unaltered. In theory, the future and the past should be mirror images. But experience tells a different story. Eggs don't uncrack. Smoke doesn't return to a matchstick. Memory only travels one way. Something enforces a temporal asymmetry that no physical law can justify. This irreversibility is rooted in entropy, the second law of thermodynamics, which decrees that systems tend toward disorder. But that law isn't fundamental. It emerges statistically. If all particles reversed, entropy would decrease. Yet it never does. The arrow of time remains mysteriously singular. The puzzle deepens when considering the universe's early state. Low entropy, highly ordered, inexplicably pristine. There is no law requiring that beginning, no boundary condition that demands such elegance. In the equations, time is a coordinate. In the universe, it is a one-way current. This conflict erodes our ability to describe causality. If physics cannot account for the origin of time's direction, then it cannot describe reality as we experience it. Reversibility in math, irreversibility in life. This fracture remains unexplained. And perhaps like time itself, it moves forward irreparably, never to be resolved by backward-looking theories. The observer effect in quantum mechanics. In quantum theory, observation is not passive. It is invasive, inescapable, and transformative. A particle exists in a superposition, multiple possible states, until it is measured. At that moment, the wave function collapses. Possibility becomes fact. But this act of observation is not just measurement, it alters the system. The outcome is shaped by the act of inquiry itself. This is not a metaphor. It's an unavoidable artifact of the theory's core structure. But who or what qualifies as an observer? A measuring device? A conscious mind? The boundary between system and observer is arbitrarily drawn. There is no physical law describing collapse, no mechanism, just an inexplicable discontinuity. The observer effect reveals a deep flaw. Reality cannot be described without referring to its interaction with knowledge. Physics, once the study of objects, becomes the study of observations. It can no longer ignore the presence of minds, or devices or interactions that define outcomes. This introduces an epistemic loop. Reality depends on observation, but observation depends on reality. No experiment escapes this trap. No theory resolves the contradiction. Every attempt to restore objectivity, hidden variables, decoherence, many worlds, merely shifts the mystery elsewhere. The observer is no longer an outsider, they are part of the equation, and that may be an error science cannot undo. The non-locality of entangled particles. Two particles become entangled. Measure one, and the state of the other is instantly determined, even if it's across the galaxy. This is not metaphorical speed. It is not faster than light in the traditional sense. It is beyond space. It violates locality, the idea that objects are only influenced by their immediate surroundings. Non-locality is not speculative. It is experimentally verified. Bell's theorem proved that no local theory can reproduce quantum predictions, and so we accept that entangled particles remain connected in a way that defies physical distance. But this connectivity cannot be used to transmit information. It is correlation without causation, a signal that is not a signal. The deeper problem is not technological but ontological. Physics presumes that reality is made of separable parts, that what happens here should not instantly depend on there. Entanglement shatters that view. It suggests that the universe is fundamentally holistic, not composed of parts but patterns, not fragments, but waves. This non-locality, essential to quantum mechanics, cannot be reconciled with the structure of space-time in relativity. One requires distance, the other ignores it. The contradiction is unresolved, and any theory that tries to fix it risks breaking both. The singularity of black holes. At the center of a black hole, equations predict a singularity, a point of infinite density, zero volume, and infinite curvature of spacetime. But infinity is not a number, it is a confession of ignorance. Singularities are not places. They are the mathematical boundary where our understanding collapses. General relativity, a theory of smooth curves and continuous geometry, breaks down at that point. Time stops, space ceases to exist, and nothing from within can be observed. The singularity is hidden, but its consequences ripple outward, defining the event horizon, dictating the hole's gravity, encoding its mass and spin. Quantum mechanics offers no rescue. It refuses to coexist with curved spacetime. The two pillars of modern physics contradict each other where they are most needed. Attempts at a quantum theory of gravity remain incomplete, speculative, or internally inconsistent. Singularities mark the failure of predictability. They suggest that nature has no flaw, no limit, no definable core. Yet they exist at the center of astrophysical giants, governing the fate of stars and galaxies. If the singularity is a lie, then everything orbiting it is built on fiction. If it is true, then physics ends at its threshold. Either way, it is an error that cannot be fixed, because no law survives its collapse. The Renormalization Paradox. In quantum field theory, particles interact through fields that extend throughout spacetime, but the math is unforgiving. Calculations involving even simple interactions spiral into infinities. Values for mass, charge, or energy that should be finite become meaningless. Renormalization is the technique invented to tame this chaos. It works by subtracting the infinities, redefining the quantities, and claiming the residual finite pieces as the observable reality. But this is not a solution. It is a controlled inconsistency, a mathematical sleight of hand. The theory predicts impossible values, then corrects them post hoc to match observations. And somehow, despite this conceptual fragility, the results are astonishingly accurate. Quantum electrodynamics, built on this paradox, predicts the electron's magnetic moment to 11 decimal places. It succeeds, but it does not explain. The paradox lies in this dissonance. A theory that is structurally flawed produces predictions of incredible precision. The map is distorted, but the landmarks align. This tension undermines the foundation of physical understanding. A theory should describe nature, not just match outcomes. Renormalization sidesteps the question of why infinities appear at all. It merely hides them under layers of procedure. Worse still, the technique breaks down in gravity. The very force that binds galaxies resists renormalization. Quantum gravity remains elusive because the infinities grow faster than they can be subtracted. The paradox is no longer just technical, it is existential. Physics has built its most successful theories on a method that admits it cannot be right. And the deeper we go, the less honest that method becomes. The quantum measurement problem. Quantum mechanics describes a world of probabilities. Particles exist in superpositions, defined not by positions or velocities, but by wave functions. Mathematical ghosts that encode every possible state. But when measured, the ghost collapses into a singular outcome. This transition, from possibility to actuality, is instantaneous, unexplained, and ungoverned by any physical law. The measurement problem is not about devices, it's about reality. Between preparation and observation, a particle exists in an undefined state. Upon observation, that uncertainty vanishes. But why? Nothing in the Schrödinger equation, the fundamental equation of quantum mechanics, accounts for this. It predicts smooth evolution, not abrupt collapse. This divide fractures the ontology of the universe. Are wave functions real? Are they merely tools for calculating likelihoods? If they are real, what mechanism decides when and how they collapse? And why is that mechanism invisible to the theory itself? Interpretations abound: Copenhagen, many worlds, pilot wave, decoherence. But none resolve the core paradox. They all smuggle in unprovable assumptions or shift the mystery to higher dimensions, infinite branches, or epistemological loopholes. The result is a science that works beautifully but cannot define what it describes. The act of measurement, the core of every experiment, remains outside the theory that governs all else. Until physics can explain why observations cause outcomes, it cannot claim to understand the universe it measures. The missing baryonic matter, ordinary matter, baryons, protons, neutrons, should make up about 5% of the universe's total energy density. This is not speculation. It's the expected outcome from models of nucleosynthesis, cosmic microwave background observations, and galaxy formation. But when we look, it's not there. Nearly half of this matter is missing. Not dark matter, not dark energy, but regular matter that should be glowing, reflecting, or absorbing light. It's not hiding in stars or planets. It's not in gas clouds, nebulae, or dust. It's not even detectable in the vast filaments of intergalactic space. Observations come up short. Simulations diverge. The universe, it seems, is lighter than it should be. The error is not in theory alone, but in observation, detection, and definition. Efforts to locate this matter in diffuse intergalactic plasma or weak X-ray emissions remain inconclusive. Each discovery accounts for a fraction, never the whole. This is not a missing object. It is a missing presence, a structural absence woven through the observable cosmos. The paradox is not merely logistical, it is epistemological. We have defined matter in terms of particles we cannot find. We have structured cosmology on equations that yield invisible components. And we persist, not because the mystery is near resolution, but because we no longer know how to ask where it went. The cosmological constant problem. The universe is expanding. That expansion is accelerating. The force behind it is attributed to dark energy, quantified by the cosmological constant. A term Einstein once introduced, then abandoned, then embraced again by necessity. It acts as a repulsive pressure woven into the fabric of space-time. But its value defies understanding. The cosmological constant should be related to vacuum energy, the baseline energy of empty space. Yet quantum field theory predicts a value so large that, if true, the universe would have torn itself apart in an instant. Observations show a much smaller number, by a factor of 10 to the 120th power. No other discrepancy in physics spans such a vast gulf between theory and measurement. This is not just a numerical error, it is a collapse of correspondence. The vacuum energy that underpins quantum field theory cannot be reconciled with the expansion of the universe. The constants do not match, the theories do not converge, and the explanations are ad hoc, scalar fields, quintessence, anthropic selection. None are supported by direct evidence. The cosmological constant problem remains the most severe fine-tuning problem in science. It suggests that our theories are not just incomplete, they are mutually incompatible at the most fundamental level. We have stitched together a picture that looks coherent from afar, but dissolves under scrutiny. The universe expands, but our understanding contracts. The failure of unification. Physics began as a fragmented pursuit. Gravity governed the heavens, mechanics ruled the earth, electromagnetism tamed lightning, and thermodynamics described heat. Over centuries, these threads were drawn together. Maxwell unified electricity and magnetism. Einstein tied space to time. The Standard Model fused the weak and electromagnetic forces. But the ultimate goal, unification of all forces into a single, coherent framework, remains unrealized. Gravity resists. Unlike the other three fundamental forces, it is not described by a quantum theory. It is geometric, continuous, and nonlinear. Every attempt to quantize it, through string theory, loop quantum gravity, or other approaches, has yielded elegant structures, but no experimental confirmation. The unification remains mathematical fiction. Even within the standard model, unification falters. The strong force mediated by gluons does not seamlessly merge with the electroweak force. The energy scales required to observe unification are unreachable. Supersymmetry was meant to bridge the gap, but its predicted particles remain unseen. The dream of a grand unified theory has become a mirage, receding with every advance. The failure is not in complexity, but in coherence. Nature refuses to reduce to a single principle. The forces remain distinct, the symmetries broken, the constants arbitrary. Our universe, so elegant in parts, resists simplicity at its core. We wanted one law to rule them all. We got four, and each tells a different story. The speed of light barrier. The speed of light is not merely fast, it is final. According to relativity, nothing with mass can reach it, and nothing can exceed it. As velocity approaches this limit, energy requirements rise toward infinity. Time dilates, length contracts, and causal order is preserved. This barrier is not technological, it is existential. It is written into the structure of space-time itself. But the universe resists obedience. Quantum entanglement allows instantaneous correlations across vast distances. Cosmic inflation suggests that regions of space once expanded faster than light. Theoretical constructs, tachyons, wormholes, warp drives, tease the possibility of breaking the limit. Yet none withstand the scrutiny of consistency. The barrier holds, and so we are confined. Not by distance, but by the inability to traverse it. The universe is accessible only in theory. In practice, it is a vast prison. No signal, no object, no particle can exceed the universal speed limit. And if it could, causality would unravel. Effects would precede causes. Time would lose sequence. The structure of reality would become recursive. This constraint shapes not just motion, but meaning. It defines what is knowable, reachable, shareable. Every scientific enterprise assumes its permanence, yet its origin remains unexplained. Why this speed? Why this asymptote? It is not a constant like others. It is a horizon of possible existence. We do not merely move below it. We are built to obey it, and that obedience may never be broken. The absence of time in quantum gravity. In the attempt to unify general relativity with quantum mechanics, theorists encountered a silent void. Time itself disappears. In canonical quantum gravity, the Wheeler-DeWitt equation, the supposed master equation of the universe, has no time variable, no clock ticks, no moments pass. The universe is described as a timeless, static configuration. All change becomes illusion. This is not a trick of interpretation. It is the direct consequence of applying quantum rules to space-time. General relativity treats time as a dimension, woven with space. Quantum mechanics treats it as a background parameter, ticking externally. When merged, the tension is irreconcilable. Time vanishes from the formalism. But experience contradicts this. We age, we evolve, stars burn, planets orbit, memories accumulate. Time is the axis of lived reality. A theory that excludes it cannot describe us, our thoughts, or our physics. It cannot account for entropy, for causality, for becoming. It explains the shape of the cosmos but denies its unfolding. Philosophers have long debated whether time is fundamental or emergent. Quantum gravity seems to settle the question, but in doing so, it nullifies its own relevance. A timeless theory cannot describe a world with clocks, and until a mechanism is found to recover time from the frozen structure of quantum spacetime, the theory remains beautiful but broken. The heat-death paradox. The universe trends toward equilibrium. Stars burn out. Energy dissipates. Entropy increases. Eventually, all gradients vanish. All processes cease. This is the heat-death, a universe of maximal entropy, devoid of structure, motion, or meaning. It is the predicted fate of all matter, all life, all computation. But entropy is statistical. It assumes the system is closed and well-defined. The universe, however, is expanding, accelerating, evolving. Its boundaries are uncertain. Its total energy may not be conserved. The assumptions behind heat death falter in the face of cosmological complexity. Moreover, the initial conditions required for entropy to rise, a low entropy beginning, remain unexplained. Why did the universe begin in such an ordered state? No law demands it. No mechanism ensures it. And yet everything depends on it. Without that improbable start, the arrow of time disappears. The paradox deepens with information. Entropy implies erasure, loss, finality. But quantum theory insists on unitarity. No information is ever truly lost. The heat death, then, is not just an end. It is a contradiction, a place where two pillars of physics give incompatible answers. We imagine a dead universe, cold and silent. But we cannot describe how it got there without breaking the theories that predict it. The heat death is not the end of time, it is the point at which time ceases to make sense. The information loss in black holes. When matter falls into a black hole, its information vanishes. Or so it seems. The event horizon marks a one-way boundary. Beyond it, all configurations of matter collapse into a singular state. From the outside, only mass, charge, and spin remain. The rest, pattern, structure, complexity, is erased. This conflicts with quantum mechanics, which forbids information loss. Every evolution must be reversible. The wave function must preserve all states. But general relativity suggests otherwise. Infalling matter alters the geometry, then disappears. Hawking radiation slowly evaporates the black hole, but this radiation is thermal, uncorrelated, uninformative. This is not a dispute of models. It is a violation of principles. One theory demands conservation. The other predicts destruction. No experiment can penetrate the horizon. No calculation can reconcile the contradiction. Attempts to resolve the paradox, firewalls, holography, entanglement, entropy, introduce deeper problems. They suggest that space-time itself must be restructured, or that information is smeared across the horizon, encoded in ways we cannot yet conceive. Each proposal saves one theory at the expense of the other. The information paradox remains unresolved. It is not about black holes, it is about the universe's capacity to remember. And if memory fails at the edge of a singularity, then perhaps it fails everywhere. The origin of mass. Mass feels fundamental. It resists acceleration. It curves space-time. It defines identity. But in the standard model, mass is not intrinsic. It is bestowed, granted by interaction with a quantum field known as the Higgs. Particles acquire mass by moving through this omnipresent medium, like swimmers through water. But this mechanism is incomplete. The Higgs explains how particles acquire mass, but not why they do so in the specific ratios we observe. The values are input manually, not derived. The theory fits the data, but offers no insight into the origin of its parameters. Worse, the Higgs itself has mass, and that mass is unstable. Quantum corrections should inflate it to Planck scale energies, far beyond what is observed. This discrepancy, the hierarchy problem, suggests a missing mechanism, a symmetry or structure we have not yet discovered. Mass also resists quantum interpretation. In a world of wave functions and probabilities, what does it mean for a particle to have mass? Is it a property of the particle or of the field? Is it real or effective? These questions remain unanswered. We have a field, we have a boson, we have equations that work. But the mystery persists. Mass, the anchor of matter, floats atop a sea of assumptions we cannot explain. The holographic principle. At the edge of a black hole, a paradox unfolds. The area of the event horizon, not the volume it encloses, determines the entropy, the total information content, of the black hole. This discovery shattered the intuitive link between information and space. It suggested that the contents of a region might be entirely described by data on its boundary. This led to the holographic principle, the proposition that all information within a volume of space is encoded on its surface. Not metaphorically, but literally. The universe, in this view, is a projection, its fundamental description residing not in the bulk of space-time, but on its outer limits. This principle, though abstract, has mathematical backing in string theory and gauge gravity dualities. The anti-de Sitter/conformal field theory correspondence shows how a higher dimensional gravitational theory can be fully represented by a lower dimensional quantum field theory without gravity. But this is not a resolution, it is a rearrangement. The holographic principle does not tell us what space is, only that it may not be what it seems. It challenges the continuity of the universe. It implies that depth is derivative, that volume is illusion. If true, this principle rewrites the ontology of physics, but we do not know if it applies to our universe, which is not anti-de sitter, and we do not understand the mechanism by which bulk and boundary communicate. It is a profound insight without a complete theory. A clue, not a key. The universe may be a hologram, but the projector remains hidden. The hierarchy problem. The weak nuclear force is inexplicably weak. Compared to gravity, it is strong. But compared to the Planck scale, where quantum gravity becomes significant, it is astonishingly feeble. The masses of elementary particles, derived from the Higgs mechanism, sit at a scale far below where naturalness would suggest. This vast gulf, 16 orders of magnitude between the weak scale and the Planck scale, is the hierarchy problem. It is not just a numerical curiosity. It points to a deep instability in our theories. Quantum corrections to the Higgs mass should pull it toward the Planck mass, unless finely tuned cancellations are applied. Such fine-tuning offends the sensibility of naturalness, a guiding principle in physics that parameters should not be delicately balanced without cause. The standard model requires that delicate tuning, and no underlying symmetry protects it. Supersymmetry was proposed to cancel the dangerous corrections. Extra dimensions, Technicolor, and composite Higgs models followed. None have been confirmed. The Large Hadron Collider found no trace of the new physics these solutions predicted, so the hierarchy remains. Why is the Higgs light? Why are the forces separated by such incongruent scales? The theory holds, but the structure beneath it is missing. We stare at the scaffolding of mass without understanding its proportions. The hierarchy problem remains, towering, unresolved. The asymmetry of antimatter. At the moment of creation, the universe should have produced matter and antimatter in equal amounts. For every proton, an antiproton. For every electron, a positron. Their mutual annihilation would have left behind only radiation. And yet, here we are. Stars, planets, organisms, all composed of matter. Antimatter is nearly absent. This imbalance, known as baryon asymmetry, violates expectations. The standard model includes CP violation, small differences in how particles and antiparticles behave, but the effect is too weak to account for the observed dominance of matter. This discrepancy is not slight. It defines the existence of everything material. The known mechanisms fail by orders of magnitude. Leptogenesis, sterile neutrinos, grand unification. These are hypothetical patches, not explanations. No experiment confirms them. No process closes the gap. The asymmetry is not a statistical fluke. It is encoded in the structure of reality. The vacuum favours one over the other, and we do not know why. Our models describe what survives, but not what was lost. The antimatter that should have mirrored us is missing, and its absence remains unaccounted for. The collapse of wave functions. A particle exists in a superposition, a spread of probabilities across potential outcomes. But when measured, the wave function collapses. Only one outcome is realised. This collapse is not predicted by the Schrödinger equation, which governs quantum evolution. It is imposed arbitrarily during observation. This discontinuity is not temporal, it is ontological. The theory evolves smoothly, deterministically, until suddenly it doesn't. Collapse introduces an irreversible, non-unitary act. It divides the universe into before and after, with no equation describing the transition. The problem is deeper than measurement. It is the chasm between potentiality and actuality. If collapse is real, it must be governed by a hidden process. If not, we must accept infinite branching worlds or relegate reality to perception alone. No consensus exists. Objective collapse models attempt to encode the transition into physical law, but they introduce new parameters and conflicts. Interpretations multiply, but none eliminate the fundamental fracture. Physics demands coherence. The collapse undermines it. It is the ghost in the machine, the unspoken leap from equation to event. And until that leap is described, quantum mechanics remains incomplete. The Arrow of Entropy. Entropy increases. Disorder rises. Systems decay from order to chaos. This is the second law of thermodynamics, and it defines the flow of time, not by clocks but by asymmetry. A broken cup does not reassemble. A cold object does not grow colder without an external gradient. Yet the microscopic laws of physics, the ones governing particles and fields, are time-symmetric. They make no distinction between past and future. They allow both. So why does entropy rise? The answer lies in boundary conditions. The early universe had remarkably low entropy. This initial state determines the arrow of time, but the cause of that low entropy is unknown. It is not required by any law. It simply was. This is not a thermodynamic detail. It is the foundation of memory, causality, and experience. The universe flows from less probable to more probable states, but only because it began improbably ordered. Every physical process inherits this asymmetry. Every explanation presupposes it. But the source remains a mystery. The arrow of entropy points forward. But nothing in the equations demands it. Time flows in one direction. Physics remains stuck in both. The Planck scale limit. At approximately 10 to the negative 35th power meters, the Planck length, space-time itself ceases to behave as a continuum. The smooth geometry described by general relativity collapses into something chaotic, quantum, and unmeasurable. This is not just a limit of current technology, it is a fundamental boundary built into the nature of the physical laws we understand. At this scale, energy densities become so extreme that gravity and quantum mechanics collide. The uncertainty principle, when applied to space-time itself, creates wild fluctuations. Distances lose meaning. Causality blurs. And no known theory can describe what remains. We are unable to probe this realm directly. Any attempt to observe it would require such energy that the process would create a black hole, concealing the very thing it tries to reveal. The Planck scale is thus a veil, a point beyond which language, theory, and measurement collapse. String theory and loop quantum gravity attempt to describe this domain, but both remain speculative. No experiment has tested their predictions. No consensus has emerged. The Planck scale represents the edge of knowability, a cliff beyond which the terrain remains permanently hidden. The universe may originate from this domain. Its deepest laws may reside there, but our access is forever bounded. The Planck scale is not a frontier to be crossed. It is a terminal condition for physical theory, the Vacuum Catastrophe. Quantum field theory predicts that even empty space teems with activity. Every point in the vacuum is alive with virtual particles, brief flickering disturbances that contribute energy to the void. When summed, this energy becomes enormous, astronomically so. Calculations suggest the vacuum should have a density of energy that would cause the universe to explode at its birth. But it didn't. Instead, the observed value of the vacuum energy, the cosmological constant, is 120 orders of magnitude smaller than predicted. No error in physics is more severe. No discrepancy is more absolute. This is the vacuum catastrophe, a chasm between theory and observation so vast that it undermines the integrity of both. Subtractions, renormalizations, and cancellations have been used to hide the divergence, but none provide a physical explanation. They are adjustments, not understandings. The problem is deeper than miscalculation. It suggests that we misunderstand the nature of energy, of space, of gravity itself. The vacuum, which should be the simplest possible state, becomes the most contradictory. Every effort to reconcile the numbers has failed. The catastrophe remains not only unfixed, but unfixable within current paradigms. The horizon problem. The universe looks the same in every direction. The cosmic microwave background, fossil radiation from the early universe, has nearly uniform temperature across the sky. But according to standard cosmology, regions of the universe separated by vast distances should not have been in causal contact. There was no time for light, or any influence to travel between them before the radiation was emitted. This is the horizon problem. The observed uniformity defies the expected limitations of speed and expansion. Without a mechanism to synchronize these regions, the homogeneity appears miraculous. Inflation theory was introduced to solve this. A rapid, exponential expansion of space in the universe's first fraction of a second. It stretches causally connected regions across the observable universe, explaining their similarities. But inflation itself is speculative. Its triggers are unknown. Its energy scale is unconfirmed, and its predictions depend heavily on assumptions. The horizon problem persists because it reveals a flaw in the causal architecture of the universe. If space expanded too fast, nothing could coordinate. If it expanded too slowly, the smoothness would be inexplicable. Either way, our models fail to justify the observed coherence of the cosmos. The flatness problem. The geometry of the universe, whether it is open, closed, or flat, depends on the balance between its expansion rate and its energy density. Observations show that the universe is nearly perfectly flat. Its spatial curvature is almost to zero, but this balance is incredibly unstable. Tiny deviations in the early universe would have grown exponentially over time, making such flatness today nearly impossible. This is the flatness problem. The initial conditions must have been tuned with extraordinary precision. A deviation as small as 1 part in 10 to the power of 60 to the power of 10 to the power of 6 to the power of 10 would have led to a radically different universe. Yet there is no known mechanism to enforce such a precise balance. Inflation theory again offers a partial fix, smoothing out the curvature through rapid expansion. But this introduces its own fine-tuning issues. The theory explains flatness only by assuming conditions that are themselves finely balanced. The flatness problem is not about geometry, it is about fragility. The universe appears delicately poised on a knife edge, without any physical justification. It implies that either the laws of nature are unnaturally precise, or that we are missing a deeper principle that keeps the cosmos in balance. The incompleteness of string theory. String theory was born from a promise, a unified theory of all fundamental forces, including gravity. It replaces point particles with one-dimensional strings, vibrating at different frequencies. These vibrations give rise to particles, forces, and interactions. The theory is elegant, mathematically rich, and internally consistent. But it is incomplete. It requires extra dimensions which must be compactified in undetectable ways. It produces not one universe, but a multiverse of possibilities. More than 10 to the power of 510 to the power of 500 configurations, each representing a different vacuum state. There is no mechanism to select the one we inhabit. No unique prediction arises from the theory's landscape. Worse, it lacks empirical confirmation. No experiment has verified the existence of strings, supersymmetric partners, or extra dimensions. Decades of theoretical development have yielded beauty without evidence. The theory remains untested and perhaps untestable. String theory does not yet qualify as physics. It is a framework searching for a foundation, a language without a fixed grammar. It aspires to describe everything, but in doing so, it explains nothing uniquely. Its incompleteness is not technical, it is philosophical. It mirrors our desire for unity, while revealing the limits of that ambition. The absence of supersymmetry. Supersymmetry was once a guiding light for modern physics. It promised to balance the equations, tame the infinities, and bridge the gap between the known and the unknown. By pairing every known particle with a heavier superpartner, it offered solutions to the hierarchy problem, dark matter candidates, and a path toward unification. The standard model seemed incomplete without it. But the universe remained silent. Despite decades of high-energy collisions at particle accelerators, like the Large Hadron Collider, no superpartners have appeared. Each non-discovery pushes the required mass scale higher, rendering supersymmetry less elegant, less natural, and increasingly contrived. The absence of supersymmetry is not merely a failure of detection, it is a philosophical fracture. The beauty of the theory, its internal coherence, is betrayed by nature's indifference. Its predictions recede into inaccessibility. It becomes untestable, and as it stretches, it begins to resemble the very problems it sought to resolve. Without supersymmetry, the standard model remains unstable. The Higgs mass remains unexplained. The forces refuse to unify. And dark matter, once expected to be a superpartner, remains without identity. Supersymmetry may still be true at unreachable energies, but in the world we can see, it has vanished, and its absence has left physics without direction. The problem of locality. Locality is the principle that an object is only directly influenced by its immediate surroundings. It defines causality. It anchors field theories. It structures space-time itself. Yet in quantum mechanics, This principle is routinely violated. Entangled particles affect each other across light years, instantaneously and without signal. Bell's theorem proves that no local hidden variable theory can explain quantum correlations. Experiments confirm this. The universe is non-local. But relativity forbids faster-than-light influence. The result is a paradox. Either we accept instantaneous influence without transmission, or we abandon the notion of independent separable systems. This tension is unresolved. Quantum field theory attempts to maintain locality through operator commutativity, but the underlying correlations remain inexplicable. Non-locality is real, and yet it cannot be used to send information. It is action without agency, correlation without causation. The problem of locality erodes the foundation of both quantum theory and relativity. It reveals that space is not what it seems, that distance may be an illusion, and that objects may not be distinct. Physics built on the scaffolding of spacetime must now contend with the possibility that spacetime itself is emergent, not fundamental. The dark matter dilemma. Galaxies spin too fast. Their stars move as if embedded in invisible mass. Gravitational lensing bends light beyond what visible matter can explain. On every scale, from clusters to cosmic filaments, there is missing mass, an unseen scaffolding that shapes the universe. Dark matter was proposed to fill this gap. It interacts gravitationally, but not electromagnetically. It does not emit, absorb, or reflect light. And yet, after decades of search, it remains undetected. Direct detection experiments yield nothing. Collider searches produce silence. Indirect observations are ambiguous. Alternative theories, MOND, emergent gravity, modified dynamics, challenge the necessity of dark matter, but they fail to match observations at all scales. The standard model of cosmology requires dark matter, yet cannot identify its nature. This is not a crisis of ignorance. It is a crisis of evidence. The mass is there, but we cannot say what it is. We build simulations, cosmologies, and predictions on a component we have never seen. The universe shaped by a shadow refuses to reveal its source. The dark energy mirage. The expansion of the universe is accelerating. Galaxies recede faster over time, not slower. To explain this, we invoked dark energy, an unknown repulsive force that permeates all space. It comprises nearly 70% of the universe's energy budget, and yet we have no idea what it is. The simplest explanation is a cosmological constant, vacuum energy, with a fixed value. But that leads to the vacuum catastrophe, an energy discrepancy beyond comprehension. Other models posit dynamic fields, quintessence, or evolving scalar potentials. None are confirmed. All are speculative. Dark energy is inferred, not observed. Its effects are subtle, statistical, woven through supernova data and the cosmic microwave background. We do not detect it. We deduce its presence through the behavior of the cosmos, then attribute causality to a force we cannot isolate. This is not discovery. It is inference stacked upon inference, a mirage stabilized by consensus. The universe accelerates, but the mechanism remains undefined. And if dark energy is not a force, but a misinterpretation of gravity itself, then our entire model may be built on sand, the unmeasurability of the universe's shape. Space is not necessarily flat. It can be curved, positively like a sphere, negatively like a saddle, or remain perfectly flat like a plane. The shape of the universe determines its fate, structure, and history. Yet we cannot measure it precisely. Observation suggests that the universe is flat or nearly so, but this measurement is constrained by our observable horizon. We cannot see beyond the light that has reached us since the Big Bang. The universe may curve on larger scales in ways we cannot detect. Topological features, loops, folds, compactified dimensions, could exist beyond our reach. Moreover, curvature measurements depend on assumptions about dark energy, matter distribution, and inflation. Tiny deviations can lead to vast interpretive errors. The universe could be finite but unbounded, like the surface of a sphere, or infinite but multiply connected. We cannot know. This is not just a limitation of tools, it is a limitation of principle. The universe may have properties we can never access. Its true shape may be encoded in regions forever causally disconnected from us. Cosmology must proceed with models, not certainties. and shape, the geometry of everything, remains unprovable, the ghost fields of quantum field theory. To preserve consistency in gauge theories, especially those with redundancies in their description of forces, physicists introduce ghost fields. These are mathematical entities that do not correspond to real particles. They exist solely within internal calculations to cancel out unphysical degrees of freedom and maintain unitarity and renormalizability. Ghosts do not appear in detectors. They do not transfer energy or momentum, yet they are essential. Without them, quantum field theories would violate probability conservation and produce nonsensical infinities. They fix the math, but they haunt the interpretation. The problem is not that ghosts are unseen. It's that their necessity reveals a deeper structural incoherence. Our theories require fake particles to make the real ones behave. It's as if a phantom architecture must be erected around the equations to keep them from collapsing under their own weight. No experiment can verify the existence of ghosts. They are purely formal, yet their removal breaks the theory. This reveals a dependence on constructs with no ontological status, mathematical ghosts, ensuring physical predictions. The contradiction is accepted, but unresolved. Quantum field theory works, but only under conditions its own components deny. Ghosts remain, not in the world, but in the equations that describe it. The frame problem in relativity. Relativity abolished the notion of absolute space and time. Motion became relative to observers, each with their own frame of reference. But not all frames are equal. In special relativity, inertial frames, those not accelerating, are privileged. They allow the clean application of Lorentz transformations and the symmetry of physical laws. But in general relativity, all frames are supposed to be equivalent. The principle of general covariance claims that the laws of physics should hold true in all coordinate systems. Yet in practice, this leads to ambiguities. Not all frames yield clear physical meaning. Some create fictitious forces. Others obscure causality. The frame problem becomes especially acute in cosmology and quantum gravity. What counts as an inertial frame in a curved, dynamic spacetime? How do you define local measurements in a universe with no global coordinate system? Observers lose their footing. Frames blur. This is not a technical issue. It is a conceptual one. Physics relies on reference frames to define velocity, acceleration, energy, and more. If those frames are undefined, or dependent on arbitrary choices, then the values become relational, not real. The frame problem is a quiet erosion of objectivity. It undermines measurement at its most basic level, the undecidability of initial conditions. Every prediction in physics depends on two elements, the laws of motion and the initial conditions. While laws are universal, initial conditions are contingent, specific values at a moment in time. They determine outcomes, trajectories, and structures. But where do they come from? And can they be known? The universe's initial conditions, the precise configuration of fields, particles, and geometry at the Big Bang, remain unknown. Worse, they may be unknowable. Chaos theory shows that small changes in starting points can yield radically different outcomes. Quantum mechanics adds further uncertainty, making exact knowledge of initial states impossible in principle. This is the problem of undecidability. Even with perfect laws, predictions fail if the inputs are inaccessible. The early universe was opaque. Observational data cannot penetrate its veil. Simulations diverge as assumptions multiply. And even in closed systems, sensitivity to initial conditions renders long-term forecasts meaningless. Physics wants to be deterministic, or at least probabilistic. But undecidable inputs create epistemic holes. They turn models into stories, not certainties. We describe how the universe evolves, but not why it began as it did. The initial conditions are not part of the theory. They are prerequisites the theory cannot explain. The problem of quantum decoherence. Quantum systems evolve in superpositions, coexisting possibilities that interfere and entangle. But macroscopic objects do not behave this way. We never see a chair in two places at once, or a cat both dead and alive. Decoherence explains this by showing how quantum systems lose coherence when they interact with the environment. The interference terms vanish, and the system appears classical. But this appearance is deceptive. Decoherence does not collapse the wave function. It only redistributes information into the environment. The superposition still exists, just no longer accessible. The system has not chosen a state, it has become entangled with countless others. This does not solve the measurement problem, it defers it. Decoherence explains why we don't see quantum weirdness, but not why specific outcomes occur. It describes the loss of coherence, but not the emergence of definiteness. It explains how possibilities become inaccessible, not how one becomes real. The problem is structural. Quantum mechanics lacks a mechanism for outcome selection. Decoherence fills the observational gap, but leaves the ontological chasm. It is an elegant bandage over a fundamental wound. The theory evolves, the observer sees, but between the two lies silence, the unrealizability of true inertial frames. In classical physics, an inertial frame is one in which objects move at constant velocity unless acted upon. It is the stage for Newtonian mechanics. In special relativity, it defines the symmetry of spacetime. But in practice, no such frame exists. Every object is influenced by gravity, acceleration, or curvature. On Earth, inertial frames are approximations. In space, they are theoretical. In a universe governed by general relativity, space-time is curved everywhere by mass and energy. No region is perfectly flat. No trajectory is perfectly straight. Inertial motion is idealized, never realized. This is more than an engineering challenge. It is a conceptual limit. All measurements are made within frames that are distorted, incomplete, or perturbed. We subtract gravitational influences, rotate coordinates, and normalize motion. But these adjustments are corrections to a fiction. If no true inertial frame exists, then the foundation of many theories rests on an approximation. The laws work because they assume something the universe never provides. Inertial frames are scaffolds without real instantiation. Useful, but imaginary. The universe curves. The lines are never straight. The boundary problem of the universe. The universe appears boundless. No edge has been found, no terminus encountered. Yet cosmology must still ask, does the universe have a boundary? If not, how can something infinite emerge from a finite origin? If so, what lies beyond? This is the boundary problem, the contradiction between an expanding universe and the absence of an external frame. General relativity allows for a closed, finite universe with no boundary, like the surface of a sphere. But unlike a sphere, we cannot step outside to view the whole. Our observations are trapped within the light cone of cosmic history. More troubling, the boundary is not just spatial, it is temporal. What lies before the Big Bang? The equations become singular, undefined. Time itself may not extend past a certain point, but a boundary in time is conceptually unstable. It implies something beyond, even if unreachable. Multiverse theories attempt to sidestep the issue by positing endless domains, but these only move the boundary elsewhere. Deeper, further, more abstract. The edge remains elusive. This is not a failure of observation, it is a flaw in the model's ontology. If the universe has a shape, it must have a context. If it is all that exists, then what is it expanding into? Physics cannot answer. The boundary problem persists because it demands a view from nowhere, and we can only observe from within. The failure of determinism at the Planck scale. At classical scales, the future follows from the present. Given enough information, the path of every object can be predicted. Determinism defines the trajectory of the cosmos. But at the Planck scale, where space-time becomes quantum, discrete, and turbulent, this certainty collapses. Quantum mechanics already challenges determinism through probabilistic outcomes. But even this is structured by wave functions and evolution. At the Planck scale, those rules break down. Time and space may no longer be continuous. Measurement itself becomes undefined. The very notion of state may dissolve. Theories of quantum gravity, whether strings or loops, suggest a reality in which classical cause and effect is an illusion. Topological fluctuations, space-time foam, or quantum geometries replace the predictable world with one of raw statistical emergence. There is no trajectory, only distribution. No before and after, only correlations. This is not mere indeterminacy, it is undecidability. A future that cannot be computed even in principle. A regime where the foundational laws are not deterministic equations, but probabilistic constraints. At this scale, determinism fails not because we lack knowledge, but because knowledge itself loses coherence. The Planck scale is the threshold beyond which cause no longer precedes effect. It is where physics ends and something else, more primal, less knowable, begins. The speed of quantum collapse. When a quantum system is measured, its wave function collapses. A set of probabilities reduces to a single outcome. But how fast does this happen? The standard theory is silent. It specifies the result, not the transition. There is no time constant for collapse, no propagation speed, no dynamics. This ambiguity is catastrophic for relativistic consistency. If collapse is instantaneous, then it violates special relativity, which forbids faster than light effects. If it is gradual, then intermediate states should be observable, but none are. If it propagates from where and how, collapse appears non-local and undefined. In entangled systems, measuring one particle affects the other instantly, regardless of distance. But no signal travels. No causal link is observed. The collapse transcends space but obeys no known law. Interpretations differ. Many worlds denies collapse entirely. Objective collapse models assign finite speeds, but none are verified. Each requires a redefinition of either time, locality, or information. This gap is not academic. It strikes at the heart of temporal structure. Without a speed of collapse, quantum mechanics lacks a temporal ontology. Events occur, but the when remains unspoken. The universe updates, but at a pace unknown and perhaps unknowable. The vacuum fluctuation instability. In quantum field theory, the vacuum's not empty. It seethes with fluctuations. Virtual particles burst in and out of existence, briefly violating energy conservation within the bounds of uncertainty. These fluctuations are real. They affect measurable forces. They are part of the fabric of everything. But they also raise a possibility: instability. If the vacuum is not the lowest possible energy state, it could decay. A bubble of true vacuum could nucleate, expand at the speed of light, and rewrite the laws of physics within it. Everything, matter, structure, constants, would be annihilated or redefined. Some calculations suggest that the Higgs field sits in a metastable state, a false vacuum. If disturbed beyond a threshold, it could tunnel to a lower energy. This is not science fiction. It is a real, if rare, prediction of standard models. The universe may not be stable, merely surviving. The deeper problem is that we cannot prove the vacuum is safe. We cannot test for stability at unreachable energy scales. We live in a state whose permanence is unguaranteed. The fluctuations that define existence may also destroy it. Instability is not imminent, but it is structural. It suggests a universe balanced precariously atop a landscape of potential energies. The void is not peace. It is risk made permanent. The entropy of empty space. Entropy measures disorder, the number of possible microstates consistent with a macrostate. It usually applies to systems with matter, gases, solids, stars. But in modern physics, even empty space has entropy. The vacuum, shaped by fields and fluctuations, possesses structure, and where there is structure, there is entropy. Black hole thermodynamics showed that horizons have entropy proportional to their area. The de Sitter universe, our own, accelerating under dark energy, has a cosmological horizon with finite entropy. This suggests that even an empty universe has a bounded information capacity, but this contradicts the traditional view. If space is empty, it should be simple. Yet it is encoded, finite, limited. It can store only so much information before coherence breaks. The entropy of empty space imposes a ceiling on knowledge, measurement, and computation. Moreover, entropy grows with time. If space has entropy, then empty space evolves. It ages. This implies that even the void is not timeless. It undergoes thermodynamic degradation. The vacuum is not static, it is entropic. The paradox is clear. How can nothing contain information? How can structure persist without matter? Physics answers with equations, but not with understanding. Empty space, once the simplest concept in science, has become the most crowded. The temporal granularity conflict. Time as we experience it flows smoothly. Seconds bleed into minutes, hours into days. But in many quantum gravity theories, time is not continuous. It is discrete, made of indivisible units. The Planck time, approximately 10 to the negative 43rd seconds. Below this scale, time ceases to divide. Events cannot be ordered. Change becomes undefined. This creates a fundamental conflict. The laws of physics, from Newton to Schrödinger to Einstein, assume continuous time. Derivatives require infinitesimals. Evolution requires smoothness. But discrete time breaks this. It replaces curves with jumps, gradients with steps. Quantum mechanics requires precise timing. Interference patterns, oscillations, tunneling, all rely on continuity. If time is granular, these effects should break down. Yet they don't. No experiment reveals temporal quantization. No deviation is detected. And yet the theories insist. The conflict is not just mathematical, it is ontological. Does time exist between ticks? If not, how does motion persist? If yes, why does granularity matter? A theory of everything must reconcile this, but none do. Temporal granularity is a necessary artifact of quantum gravity, but it shatters the framework of continuous change. The clock ticks, but we don't know how or when or if it really ticks at all. The uncertainty of quantum histories. In classical physics, the past is fixed. A trajectory is traceable, a cause retrievable. But in quantum mechanics, histories are uncertain. A particle does not follow a single path, it follows all paths. The Feynman path integral formalism sums over every possible trajectory, each weighted by a complex amplitude. This means the past, like the future, is probabilistic. Observations fix endpoints, but the intervening route is a tapestry of possibilities. There is no one true history, only a superposition of what might have occurred. In the decoherent histories approach, the universe is described not by a single timeline, but by a set of consistent but mutually incompatible narratives. Each is a valid account, yet they contradict one another. The truth is not singular, it is statistical. This destroys the notion of objective record. Memory, causation, even identity become entangled in a cloud of possible pasts. The past is not immutable. It is reconstructed by observation, just like the future. We do not live in a universe that has happened. We live in one that is happening, probabilistically, in all directions. The idea of a singular history collapses under the quantum view. What is left is coherence without certainty, the causal disconnection of cosmic regions. The observable universe is vast but finite. Beyond its edge lie regions forever unreachable, not just in practice but in principle. Light from them will never reach us. They are causally disconnected, isolated by the accelerating expansion of space. This disconnection fragments the cosmos. It means the laws we observe may not apply universally. The constants, fields, even the vacuum structure could vary beyond our horizon. We have no way to test this. No experiment can cross the divide. Inflationary models exacerbate the problem. They suggest a multiverse, where bubble universes form with different parameters. Each is causally sealed. We inhabit one, we will never access another. This undermines the ambition of physics to describe the whole. We model a sliver and generalize. But the unobservable regions may differ fundamentally. And if they do, the very idea of universal laws becomes parochial. Causal disconnection is not a technical boundary. It is a fracture in ontology. We cannot know if our laws are global or local. We cannot confirm the uniformity of reality. The universe may be one, but it is forever fragmented. The time-symmetric laws with asymmetric reality. The equations of physics are mostly time-symmetric. Whether moving forward or backward, the math remains unchanged. Schrödinger's equation, Newton's laws, even general relativity, all indifferent to direction. Yet reality is not. We remember the past, not the future. Eggs break but do not unbreak. The sun will burn out. It will not reignite. This asymmetry is real, empirical, and universal. The only known arrow comes from thermodynamics. Entropy increases, defining a direction, but entropy is statistical, not fundamental. It emerges from boundary conditions, the low entropy origin of the universe. Why that origin occurred is unknown. Time symmetry in law, time asymmetry in fact. This is not just a gap, it is a contradiction. If the laws allow reversal, why does reality forbid it? Why is the universe biased toward decay? Some propose that time's arrow is anthropic. We observe it because we evolved in a low entropy region. But this is no answer. It is an admission of ignorance. The laws and the world they describe refuse to align. Time is not a mirror. It is a current. The equations deny this. The universe insists on it. The loss of objectivity in particle physics. In classical physics, properties exist independently of observation. A particle has a position. An object has momentum. Reality is objective, observer independent. But in quantum mechanics, this clarity dissolves. Properties are not possessed, they are inferred. A particle has no definite position until measured. The measurement itself defines the value. This destroys objectivity. The wave function represents knowledge, not ontology. Reality becomes epistemic, dependent on what is known, not what is. The observer, once external, becomes part of the system. The distinction between subject and object breaks down. Experiments like the delayed choice quantum eraser show that choices made in the present affect which histories appear in the past. This is not causality. It is interpretive collapse. Reality is shaped by interaction, not inherent existence. Every attempt to restore objectivity, hidden variables, pilot waves, many worlds, fails to do so without cost. They either add complexity or deny determinacy. The particle is here and there, it spins up and down, but only when we look. Physics once aimed to describe the world as it is. Now it describes the world as it appears. The loss of objectivity is not just a feature, it is a failure. The universe exists, but no one can say how until it is seen. The energy-time uncertainty disruption. The uncertainty principle is foundational in quantum mechanics. Position and momentum cannot both be known with infinite precision. Energy and time, too, share a similar relation. But while position and momentum are canonical variables, symmetrical within quantum formalism, energy and time are not. Time is not an operator in quantum mechanics. It is a parameter, an external marker. This makes the energy-time uncertainty relation structurally different, less rigorous, more ambiguous. It lacks a clean derivation. Its interpretations vary depending on context. Decay rates, energy spreads, transition probabilities. The deeper disruption is conceptual. If time is not a quantum observable, then quantum mechanics is incomplete in its description of change. Energy fluctuations allowed by uncertainty, permitting virtual particles and vacuum instabilities, occur over undefined intervals. But what governs those intervals? The theory does not say. This mismatch creates holes in our understanding of temporality, decay, and causality. It affects everything from particle lifetimes to the cosmological constant. It blurs the line between real and virtual. And it reveals that time, unlike other physical quantities, remains outside the quantum realm. The energy-time uncertainty principle works. It predicts, it describes, but it is not derived from the same foundations. It floats, unanchored. That asymmetry fractures the coherence of quantum theory at its core, the artificiality of renormalization. Quantum field theory predicts infinities. When calculating interactions, integrals diverge. Charges become infinite. Masses lose definition. To cope, physicists invented renormalization, a procedure to subtract infinities and extract finite results. It works, it delivers predictions with stunning accuracy, but it is not natural. Renormalization is a mathematical ritual, not a physical process. It involves redefining parameters, introducing cutoffs, and discarding terms that misbehave. It is guided by consistency, not by cause. There is no physical entity doing the renormalizing. It is an external imposition. This artificiality undermines the ontology of field theory. A theory that generates infinities is, by itself, nonsensical. That it becomes sensible only after an arbitrary adjustment reveals a deep inconsistency. It suggests that our models are descriptive, not explanatory. Effective tools, not fundamental truths. Gravity notably cannot be renormalized. This singular fact hints at a breakdown in the whole framework. If renormalization is required to make a theory finite, then perhaps the infinities are symptoms of an incorrect foundation. We live in a universe of finite measurements, but we describe it with theories that produce infinities, then erase them by hand. Renormalization works, but only by pretending the wound it hides is not fatal. The limits of simulation hypotheses. The idea that reality might be a simulation, a vast computational structure emulating a physical universe, has gained cultural and philosophical traction. It proposes that our cosmos, with its rules and constants, is the output of a machine. But this hypothesis, while provocative, reaches an epistemic dead end. Any observable phenomenon attributed to simulation is indistinguishable from natural law. The simulation hypothesis makes no falsifiable predictions. It cannot be confirmed, because every piece of evidence can be interpreted as either genuine or rendered. Worse, it introduces an infinite regress. If our world is simulated, what simulates the simulators? And what computational substrate hosts their world? At some point, reality must be real. The simulation hypothesis shifts the burden of explanation but resolves nothing. It also fails to address physical problems. What is the processor of the universe made of? What defines its clock cycle? How are quantum indeterminacies computed? The model relies on metaphors from human computing, but the universe does not behave like a digital machine. In physics, the simulation hypothesis is inert. It adds no clarity, introduces no constraints, offers no mechanism. It is philosophy disguised as science fiction, a myth of modern logic, impressive, recursive, but structurally void. The unpredictability of chaotic systems. Chaos is not randomness, it is sensitivity to initial conditions. In chaotic systems, infinitesimal differences in starting values yield exponentially diverging outcomes. Weather, turbulence, planetary motion. These are deterministic systems with behavior that defies long-term prediction. The problem is not that we lack equations, it's that the solutions are unstable. Precision becomes meaningless. Forecasts collapse into uncertainty. Not from lack of theory, but from the nature of the systems themselves. This unpredictability challenges the dream of determinism. Even with perfect laws, the future can be unknowable. Chaos theory reveals that predictability is not guaranteed by mathematics. The line between order and disorder is sharp, invisible, and often crossed. Quantum mechanics adds further layers. Decoherence in chaotic quantum systems creates mixtures so complex that the classical world emerges from entangled unpredictability. Predictive power decays. The initial conditions become unreachable even in principle. Physics assumes that understanding the parts yields control of the whole. But chaos invalidates that. It reveals a boundary beyond which knowledge cannot extend. The system is known. Its evolution is not. The fractal nature of physical constants. Physical constants, Planck's constant, the speed of light, the gravitational constant, are considered fixed, universal values. They define the structure of equations and the behavior of particles. Yet we don't know why they have the values they do. We insert them by hand. We measure, not derive. Some theories suggest these constants may vary, over time, across space, or within different cosmological domains. Others suggest they arise from deeper layers, emergent from more fundamental structures. But in every case, the constants are treated as boundaries, immutable facts framing mutable laws. Yet patterns appear. In the fine structure constant, in mass ratios, in charge distributions, fractals, self-similarities, unexplained symmetries. Some physicists explore numerology, others reject it as coincidence, but the regularities persist. If constants are not constant, or if they encode patterns we do not understand, then our laws are built on empirical shadows. A fractal structure of interrelated values hints at hidden dimensions, unknown symmetries, or deeper computational mechanisms. The constants are scaffolds for physical theory, but we cannot explain their origin, cannot predict their value, cannot derive their necessity. If they are truly fundamental, they are unknowable. If they are not, they are signs of a deeper theory we do not yet possess. The logical circularity of self-referential systems. Self-reference lies at the heart of paradox. In logic, it births contradiction, statements that refer to themselves, like the liar's paradox, undermine the coherence of formal systems. In physics, self-reference is less obvious but equally insidious. Theories describe the universe, but they are constructed within it. Observers model systems of which they are a part. Instruments measure conditions they help define. This feedback creates circularity. Cosmological models attempt to explain the totality, yet the models themselves are shaped by the cognitive and observational limitations of the beings inside that totality. A physical law is inferred from phenomena, which are filtered through assumptions built on those same laws. There is no external vantage point. Quantum mechanics exemplifies this loop. Measurement outcomes depend on the observer, but the observer is governed by quantum rules. Information theories model information within systems that are themselves informational constructs. Foundations collapse into recursion. This is not a bug of language or interpretation. It is a structural limit. A self-contained system cannot explain itself completely without contradiction or incompleteness. Gödel proved this for mathematics. Physics may be no exception. We seek objective truth, but our tools, minds, and measurements are entangled with the very phenomena we analyze. Self-reference binds us to uncertainty, not in predictions, but in meaning, the inaccessibility of pre-Big Bang physics. The Big Bang marks the boundary of observable time. Beyond it, before it, our theories fail. The density and temperature reach extremes where general relativity collapses and quantum effects dominate. But no complete theory of quantum gravity exists. The result is a wall, not of matter but of knowledge. Cosmologists speculate, a bounce, a cyclic model, quantum tunneling from nothing. Each proposes a pre-Big Bang reality, but none are empirically accessible. No light, no signal, no relic survives that primordial veil. The observable universe begins after inflation. Everything before is reconstructed guesswork. Even the language breaks down. What does before time mean? What does it mean to say something happened when time did not yet exist in a meaningful sense? Our concepts of causality and sequence are rooted in the structure of space-time, a structure that the Big Bang rewrites. This is not just an observational boundary, it is an epistemological one. The universe hides its own birth. Physics can describe the evolution of reality. It cannot yet describe its emergence. The origin, if it exists, is unreachable, not due to scale but due to the collapse of theory itself, the broken symmetries of the early universe. Symmetry is elegant. It simplifies equations, reveals conserved quantities, and guides the formulation of physical law. At high energies, the early universe may have exhibited perfect symmetry among the fundamental forces. But as it cooled, those symmetries broke. Forces split. Particles differentiated. Asymmetry was born. These symmetry breakings are necessary to explain the world we see. Without them, there would be no atoms, no structure, no directionality. But the mechanism of symmetry breaking, how and why specific patterns collapsed, is largely unknown. Spontaneous symmetry breaking provides a mathematical tool, but not an ontological account. Worse, the breaking appears arbitrary. The strengths of the forces, the masses of the particles, the constants of nature, all emerge from this early divergence, yet remain unexplained. The Higgs field is invoked, but its structure and origins are still obscure. Grand unified theories predict patterns that observations have not confirmed. Symmetry breaking is not clean. It leaves relics, topological defects, imbalance, anomalies. Many are never found. Others contradict observations. The transition from a symmetric vacuum to a broken reality is central to modern physics, and still deeply mysterious. The universe did not unfold smoothly. It fractured, and we are built upon the shards. The problem of the observer in cosmology. Cosmology seeks to describe the universe as a whole, but every observation is made from a specific vantage point, a single world line within an expanding, anisotropic, and partially observable cosmos. This introduces the observer into what was meant to be an objective science. We cannot step outside the universe to see its totality. We cannot rerun its history. We measure redshifts, background radiation, and light from distant galaxies, but always through the lens of our location, motion, and limitations. The result is a map whose accuracy depends on assumptions we cannot test. Cosmic microwave background data must be cleaned of local effects. Distances depend on standard candles and cosmological models. Each step introduces observer-dependent factors. Even our idea of a homogeneous universe is based on averages taken from a limited view. Quantum cosmology compounds the issue. If the universe is a quantum system, then the observer must be included in the wave function. But then, who collapses the wave? What constitutes a measurement? The act of observing becomes part of the cosmos being described. The observer problem in cosmology is not an error, it is a limit. We are inside the system we seek to explain, and that changes everything. The irrelevance of absolute time. In Newtonian mechanics, time is absolute. It flows uniformly, independent of events. It provides a fixed backdrop against which motion occurs. But relativity discarded this. Time became local, variable, intertwined with space. It dilates near mass, slows with velocity, ceases to be universal. Quantum mechanics, however, clings to absolute time. Schrödinger's equation evolves states with respect to a single external parameter, time. This creates a conceptual rift. Time is dynamic in one framework, static in another. Neither integrates the other. In quantum gravity, time vanishes entirely. The universe is described by a timeless wave function. Evolution becomes illusory, and yet our experience, our physics, our measurements are rooted in duration and sequence. This is the irrelevance of absolute time. It does not exist in the physical universe, yet remains essential in the tools we use to describe it. We solve equations with respect to time while denying its objective presence. It is both central and absent. Time may not be a thing. It may be emergent, relational, contextual. But physics is not ready to relinquish it. The equations need it, even if the cosmos does not. The invisibility of multiverse branches. In the many worlds interpretation of quantum mechanics, every possible outcome of a quantum event actually occurs in a branching, ever-splitting multiverse. Each universe contains a different version of events, histories, and observers. But none of these branches can interact. They are causally isolated, observationally inaccessible, and forever hidden from one another. This leads to a profound invisibility. The theory posits an infinite ensemble of realities to explain a single outcome, but offers no way to confirm their existence. There is no experimental path to detect another branch. No signal can cross the boundaries. The other versions of yourself, the alternate histories, the uncollapsed paths, all are ghosts in the formalism. Yet the theory claims to be complete. It denies wave function collapse by replacing it with unobservable multiplicity. It resolves nothing, only defers the question: what selects the observed path? The answer is that all paths are realized, but none are ever known. This is not a philosophical elegance. It is a physical emptiness. The multiverse explains everything, and therefore nothing. It has no predictive power. It cannot be falsified. It cloaks its own irrelevance in abstraction. Branches exist, perhaps. But if they are unreachable, undetectable, and untestable, then their existence is metaphysical, not physical. The many worlds remain many, but invisible. And physics cannot see them. The discreteness versus continuity paradox. Modern physics is divided. At macroscopic scales, reality is modelled as continuous. Fields stretch smoothly across spacetime. Motion is described with calculus. Geometry is curved, but unbroken. Yet quantum mechanics reveals discreteness, quantized energy levels, finite measurement resolutions, and granular behaviour at the smallest scales. The paradox is that both models succeed. Continuity predicts gravity, fluid flow, electromagnetic fields. Discreteness governs atoms, radiation, and information. But they are incompatible. A truly continuous system has infinite degrees of freedom. A discrete system has none beyond its elements. The transition between the two remains unexplained. In quantum field theory, the continuum is kept, but tamed with cutoffs and renormalization, artificial adjustments that hide infinities. In quantum gravity, discreteness is postulated. Space itself is made of finite loops or strings. But no unifying model has reconciled these two worldviews. Are particles points or vibrations? Is space smooth or pixelated? Do fields exist between measurements? These questions persist because the models both work separately. Together they conflict. The universe seems to be continuous in appearance, discrete in structure. But we cannot bridge the two without tearing the theories that describe them. The paradox remains unresolved, a universe both seamless and fragmented. The limits of gravitational information. Gravity, unlike other forces, is not easily shielded or localized. It is geometric, an effect of space-time curvature. But this very nature limits how information can be stored and transmitted within a gravitational field. The holographic principle suggests that the maximum amount of information inside a volume is proportional to its boundary, not its interior. This is profoundly counterintuitive. In black hole physics, the Bekenstein-Hawking entropy formula confirms this. A black hole's entropy scales with the area of its horizon. This implies a fundamental cap on information density. No matter how large the volume, the boundary constrains the total information it can contain. This is not just a quirk of gravity, it is a structural limit. It suggests that gravity erases information, or at least obscures it behind horizons. Efforts to recover lost data, such as the black hole information paradox, remain unresolved. Quantum mechanics demands unitarity. Gravity resists. The deeper issue is that information cannot be localized in a gravitational field without creating distortions. Observation becomes action. Measurement warps what it measures. Unlike other forces, gravity embeds the observer in the observed. This limits not just what we can know, but what can be. Gravitational systems hold less information than their appearance suggests. They are vast but mute, full of motion but partially blind. And that blindness is not a flaw. It is a rule, the loop quantum gravity fragmentation. Loop quantum gravity, LQG, is one of the leading attempts to quantize spacetime. It replaces the smooth geometry of general relativity with a network of discrete loops, tiny quantized units of area and volume. Space becomes granular. Time emerges from change within this network. The theory is background independent, finite and free of infinities. But it is also fragmented. The spacetime it describes is a tapestry of disconnected nodes and links, with no continuum between them. Geometry is reconstructed from algebraic relations, not from smooth metrics. This causes trouble when matching predictions with the classical world. Recovering general relativity from LQG remains unsolved. The semi-classical limit, how smooth space emerges from discrete structures, is mathematically opaque. The dynamics of time evolution, encoded in spin foams, are not yet predictive. The theory lacks clear experimental signatures. Moreover, LQG does not unify the forces. It quantizes gravity alone. It sidesteps string theory's higher dimensions and symmetry structures, gaining simplicity at the cost of completeness. It describes quantum geometry, but not the full universe. LQG may be internally consistent, but it risks being a theory of something that no longer exists at observable scales, a fragmented description of a continuum that hides its pieces. Without a path back to the world we see, its loops remain closed. The computational incompleteness of nature. Physics aspires to be computable. That is, given a set of initial conditions and laws, one should be able to calculate the future state of a system. But computation itself has limits. Gödel's incompleteness theorems show that within any formal system, there are truths that cannot be proven. Turing's halting problem shows that some outcomes are undecidable. Information theory imposes ceilings on knowledge transfer. These limits apply to nature. Certain physical systems, especially those involving quantum chaos, turbulence, or infinite complexity, may be computationally irreducible. Their behavior cannot be predicted without simulating every step. There are no shortcuts. The system is its own fastest description. This means the universe may contain processes that no theory can compress, no formula can predict. The future becomes not only unknown but unknowable. Determinism persists in theory, but vanishes in practice. Even the structure of physical law may be incomplete. Some patterns may be undecidable within our mathematical framework. Some constants may be uncomputable. Nature, it seems, is not a machine running a clean algorithm. It is a substrate of information with no guarantee of coherence. Computational incompleteness does not halt physics, but it delimits its scope. It shows that understanding may not mean explaining, and that explanation may have no end. The boundary conditions of the universe. Every physical equation requires boundary conditions, constraints that define how a system begins or ends. But when the system in question is the entire universe, what constitutes a boundary? Where is the edge, and what sets the initial values? Cosmology uses models to simulate evolution, but each requires assumptions about starting conditions. The density of matter, the uniformity of radiation, the curvature of space, none are derived, they are imposed. Without them, the equations remain unsolvable, their solutions undefined. But there is no external environment to set these boundaries. The universe is not embedded in a larger system. It contains all observers, all clocks, all reference frames. This makes the very concept of boundary metaphysical, not physical. Attempts to resolve this, such as the no-boundary proposal or quantum cosmology, offer mathematical frameworks but no empirical access. We cannot test conditions beyond the horizon of observability. We cannot rerun the origin. The boundary conditions are forever out of reach. The result is circularity. We explain the universe using equations that require unknown inputs. The initial state is not predicted. It is guessed. The laws describe how things evolve, but not why they began as they did. The boundary is not a place. It is an unanswered question. The infinite regression of physical laws. We ask, why does a law of nature exist? And then, why that law, not another? For every explanation, a deeper framework is assumed. This leads to an infinite regression. Laws derive from principles, principles from meta-laws, and so on. The search for fundamental explanation becomes endless. This is not a flaw in logic, but a structural property of theoretical systems. Any law can be questioned. Any axiom can be challenged. In mathematics, axiomatic foundations must eventually be accepted without proof. In physics, we face the same dilemma. If laws are fixed, why? If they evolve, how? If they emerge from deeper structures, what governs those structures? Multiverse theories attempt to resolve this by positing a landscape of laws, each universe with its own set. But then what governs the multiverse? No theory avoids the chain. Each step deeper introduces more assumptions, more unknowns. At some point, explanation ceases. The origin of physical law may not be knowable. It may not exist. We seek the root of reality, but every answer is a branch. The trunk remains hidden, or absent. The untraceability of causal origins. Causality is the backbone of physical reasoning. Every effect has a cause. Every event is linked to prior states, but in quantum mechanics this linearity breaks. Events occur probabilistically without clear antecedents. In cosmology, initial causes are unobservable. In thermodynamics, entropy obscures reversibility. This creates a horizon beyond which causality fades. Quantum fluctuations generate particles with no prior trigger. Inflation stretches regions beyond causal contact. Black holes hide causal paths behind horizons. Even within classical systems, chaotic dynamics erase traceability. The butterfly effect ensures that the smallest perturbation becomes undetectable over time. The origin of any specific event becomes unknowable, not because it lacks cause, but because the cause is lost in complexity, indeterminacy, or space-time geometry. The Big Bang itself may have no cause in any conventional sense. It marks the end of traceability, not the beginning of events. We build histories from data, models from sequences. But these reconstructions fail at the extremes. Causality becomes inference, not fact. The arrow remains, but the origin dissolves. The universe moves forward, but its steps cannot all be retraced. By the existence of unobservable dimensions. String theory requires extra dimensions, 10 or 11 total depending on the variant. These dimensions are compactified, curled up at scales too small to detect. They determine the vibrational modes of strings, which in turn define the properties of particles and forces. But these dimensions are unobservable. No experiment has confirmed their existence. Their shape, topology, and influence are inferred from mathematical consistency, not empirical verification. And because their size is presumed to be near the Planck scale, direct detection may be impossible. This introduces a crisis of interpretation. If fundamental features of the universe are forever inaccessible, how do we justify the theory that invokes them? Compactified dimensions become parameters to be tuned, not structures to be revealed. They explain nothing uniquely. They predict nothing definitively. The notion of extra dimensions may be correct, but if they cannot be seen, measured, or tested, they remain speculative, elegant but untouchable, real but unverifiable. They become scaffolding for a model, not for reality. Physics aims to describe what is, but in invoking unobservable dimensions, it risks describing only what can be imagined. The delusion of point particles. In the standard model, elementary particles are treated as point-like, objects with no spatial extent. This simplifies the equations, avoids internal structure, and aligns with experimental data. But it also creates infinities. Point charges produce infinite self-energy. Point masses collapse spacetime. Renormalization hides these infinities. But the physical contradiction remains. Objects with no size exert force, carry mass, and interact with fields. The notion of a point particle is a mathematical abstraction, not a physical entity. Attempts to replace points with extended objects, strings, loops, branes, introduce complexity without resolution. No evidence confirms that particles have structure. No observation disproves it. The point persists not because it is true, but because it is tractable. But this tractability hides a lie. Real objects cannot be zero-dimensional. A point has no volume, yet defines interaction. It produces curvature without geometry. It creates force without surface. The model works, the concept does not. We accept point particles because they compute. But what they are remains a fiction, a useful fiction, a necessary delusion, the non-existence of a true vacuum. The vacuum is not void. It seethes with fluctuations, virtual particles, and latent fields. But the idea of a true vacuum, a state of absolute lowest energy, completely stable and unchanging, has become suspect. Quantum field theory allows for metastable vacua, false minima that appear stable but can decay under rare conditions, collapsing into a deeper state. The Higgs field may sit in such a metastable configuration. If disturbed beyond a critical threshold, it could tunnel to a lower energy vacuum. This event would propagate at light speed, destroying all known structures, rewriting the laws of physics within the new vacuum state. But more fundamentally, every proposed vacuum depends on an assumed background, fields, dimensions, constants. Each nothing is structured by something else. The vacuum is layered, not fundamental. Every time we define it, we later discover it is not the lowest possible state. This infinite regress suggests that a true vacuum, if it exists, can never be verified. It is defined by its inaccessibility. If a lower state exists, we won't know until it consumes us. The vacuum becomes not a baseline, but a precarious plateau. No field theory can rule out a deeper minimum. No experiment can confirm final stability. The vacuum's not ground. It is scaffolding, and the ground may never be found. The self-destructiveness of grand unification. The dream of grand unification is elegant. At high energies, all fundamental forces merge into a single interaction, governed by a unified field. This principle would explain the apparent differences between electromagnetism, the weak force, and the strong force as consequences of symmetry, breaking at low energies. But the mathematics of unification introduces fatal instabilities. Proton decay becomes inevitable in most GUTS, yet it has never been observed. Supersymmetry is often required to stabilize the unification, but no supersymmetric particles have been detected. The coupling constants must converge with precision, yet they do not unless finely tuned. More disturbing is that many guts predict vacuum instabilities, monopoles or cosmological remnants that would dominate the universe, but are absent. These theories suggest conditions that, if true, would have destroyed the universe long before galaxies formed. Unification, it seems, is structurally destructive. It collapses into complexity, unpredictability, or contradiction. It explains symmetry by introducing more parameters. It achieves elegance through peril. The very act of merging forces tears the theory apart. The universe appears unified in form but broken in substance. Grand unification may be real at unreachable energies, but its implications remain unfulfilled, and its structure unstable. The breakdown of mathematics at singularities. Mathematics is the foundation of physics. It models motion, fields, interactions, and space. But at singularities, points of infinite density, zero volume, or undefined curvature, mathematics fails. Equations diverge. Predictive power collapses. General relativity predicts such singularities at the centers of black holes and at the origin of the universe. These are not just technical errors, they are warnings. Singularities are not regions where physics stops. They are boundaries where our mathematical language becomes meaningless. The curvature becomes infinite, but infinity is not a number. It is a symbol of absence. Quantum gravity may one day resolve these infinities, replacing them with finite structures. But no such theory exists yet. And even proposed resolutions, like bouncing cosmologies or loop quantum geometries, struggle to recover predictability at these extremes. The singularity is not a point in space. It is a hole in theory, a place where explanation implodes. The laws that govern the universe fail at its most intense locations. Mathematics, once the precise tool of description, becomes silent. And in that silence, the universe speaks nothing we can understand. The problem of infinite sets in physics. Infinity is a powerful tool in mathematics. It allows for limits, integrals, and continuity. But in physics, infinity becomes perilous. Infinite mass, energy, or density are unphysical. Yet they appear in calculations, often requiring renormalization, subtraction, or redefinition. Infinite sets, such as those used in quantum field theory, modes of oscillation, virtual particles, or space points, introduce problems of convergence and definition. How can a finite universe contain an infinite number of degrees of freedom? How can computation proceed over uncountable sets? Mathematics allows infinity to exist within axioms. Physics does not. All measurements are finite. All observations bounded. Every infinite term in an equation signals a breakdown of correspondence between model and reality. The universe may be vast, but it is not infinite in what it can contain, describe, or support. Space is quantized, energy bounded, entropy capped. The use of infinite sets is a convenience that fails at the limits of scale. Infinity is not a fact of the universe. It is a symbol of the limits of our imagination and our tools, the observer-dependent nature of spacetime. In relativity, spacetime is not fixed. It is curved by mass, altered by energy, shaped by motion. But more profoundly, it is observer-dependent. An event's coordinates vary by frame. Time dilates, length contracts, simultaneity disappears. There is no absolute now. In quantum mechanics, the observer further disrupts objectivity. Measurement alters state. Observation defines outcome. When combined, these frameworks suggest that even spacetime itself may be subjective, defined by the relations among observers and systems, not by a universal background. This relational view undermines classical notions of space and time as containers. If events are only defined relative to observers, then the universe is a network of perspectives, not a map. The consequence is not merely philosophical, it is structural. It means there is no master coordinate system, no absolute clock. Every measurement is contingent, every position a matter of context. The fabric of reality is relational, not geometric. Space and time do not exist independently. They emerge from interaction, entanglement, and motion. The observer is not in space-time. The observer defines it. The paradox of quantum non-cloning. Quantum mechanics forbids the copying of arbitrary quantum states. This is the non-cloning theorem. No machine, no operation, can produce an exact duplicate of an unknown quantum state. This is not a limitation of technology. It is a mathematical consequence of the linearity of quantum theory. But this restriction introduces paradoxes. In classical systems, duplication underpins information transfer, backup, and preservation. In quantum systems, the impossibility of perfect copying means that information is fragile, localized, and fundamentally volatile. It cannot be copied. It must be transferred, entangled, or collapsed. This restriction shapes the architecture of quantum communication, computation, and encryption. But it also raises unresolved questions about measurement and memory. If a quantum state cannot be copied, how is it remembered by a measuring apparatus? How can it leave a trace? In quantum teleportation, information is transmitted by destroying the original, proof that cloning is not just impractical, but conceptually forbidden. This makes the quantum world discontinuous in a way that resists intuition. Identity, persistence, and replication are lost. The non-cloning paradox reveals that information in quantum mechanics is not like classical data. It is contextual, holistic, and non-replicable. The past cannot be perfectly stored. The present cannot be duplicated. The future cannot be fully known. The contradiction of virtual particles. Virtual particles populate the vacuum. They appear in Feynman diagrams, mediate forces, and explain observable effects like the Lamb shift and the Casimir force. But they are not real in the conventional sense. They do not satisfy the energy-momentum relation. They cannot be detected. They exist only in the mathematics of perturbation theory. This introduces a contradiction. Entities that do not exist in physical space produce real, measurable consequences. They are not particles, but terms in a series. Not observations, but artifacts of calculation. And yet we treat them as explanatory mechanisms. This duality undermines the ontological clarity of quantum field theory. What is real if not observable? What is effective if not present? Virtual particles are invoked to make sense of forces. Photons for electromagnetism, gluons for the strong force. But none exist during the interaction. They are ghosts in the math. And yet the theory collapses without them. This reveals a foundational incoherence. Physics relies on things it denies, models behaviours it deems impossible, and explains reality with unreal components. Virtual particles are not false. They are not true. They are necessary illusions. The absence of energy conservation in cosmology. In local physics, energy is conserved. It moves, transforms, dissipates, but never vanishes. This principle underlies every experiment, every calculation. But in cosmology, energy conservation fails. The expanding universe, governed by general relativity, does not preserve total energy. Photons stretch as space expands. Their wavelength increases, their energy decreases. But that energy does not go elsewhere. It is lost. The gravitational field, unlike other fields, has no local energy density. There is no global time coordinate to anchor conservation. This breaks the link between symmetry and conservation, defined by Noether's theorem. Time translation symmetry yields energy conservation. But the universe has no global symmetry. It evolves, and in that evolution, energy becomes ambiguous. Dark energy complicates this further. It accelerates the expansion, adding to the universe's energy without a source. The system grows more energetic without input. The laws work locally but not globally. This is not an error. It is a structural feature of curved space-time. But it erodes one of physics' most sacred principles. The universe, it seems, does not conserve energy. It only pretends to in small, well-behaved corners. The breakdown of causality in wormholes. Wormholes are hypothetical bridges in space-time, shortcuts between distant regions or even different moments in time. Allowed by general relativity, under specific exotic conditions, they introduce not just spatial, but temporal discontinuities. If a wormhole connects one point to another in the past, closed time-like curves arise, paths that loop through time. This enables paradoxes, the grandfather paradox, information from nowhere, causal loops without origin. Such violations are not artifacts of bad models. They are legitimate solutions to Einstein's field equations. But they are physically unstable, requiring negative energy or exotic matter to remain open. Even if they could exist, their implications would shatter causality. Attempts to resolve this through chronology protection conjectures or quantum back reaction introduce their own uncertainties. The universe seems to resist such structures, but does not forbid them outright. If wormholes exist, even as transient quantum structures, then cause and effect are no longer fundamental. Information could precede its own generation. Events could self-generate. Time becomes a loop, not a line. Causality is a pillar of physical law. Wormholes are its undoing, the ontological ambiguity of fields. Fields are the bedrock of modern physics. Every particle is an excitation of an underlying field. Electrons, photons, quarks, all are ripples in quantum fields that pervade space. Yet these fields are never directly observed. We detect their excitations, not their substance. This creates ontological ambiguity. Is the field real, or is it a mathematical construct? Does it exist independently, or only as a framework for describing interactions? Fields are defined over space-time points, yet at small scales, space-time may not exist in any meaningful sense. Moreover, fields are infinite in extent. They carry energy, yet have no boundary. The vacuum itself is a field configuration. But what defines its baseline? What shapes its topology? These questions remain unanswered. Different formulations of physics describe fields differently: classical, quantum, gauge theoretic. Each reinterprets the field's meaning, yet none resolve its essence. Is it substance? Is it relation? Is it merely information? The field is everywhere yet nowhere. It defines particles but defies definition. It is not a thing, but it is everything. The blindness of physics to consciousness. Physics describes the external world: particles, fields, forces, structures. It quantifies interactions, maps space-time, predicts motion. But consciousness, subjective awareness, experience, selfhood, remains entirely absent from its equations. This is not an oversight, it is a structural void. The framework of physics assumes observers, yet never explains them. Measurements are made, but the entity that perceives the outcome is never modelled. Even in quantum mechanics, where observation affects systems, consciousness is treated as an abstract function, not a phenomenon. There is no variable for awareness, no equation for qualia, no field that encodes the sense of being. Consciousness resists reduction. It cannot be measured without being altered. It cannot be modelled without being presupposed. Attempts to bridge the gap through neuroscience, integrated information theory, or panpsychism remain philosophical. No physical theory includes the first-person perspective, and yet all observation, all science, begins with it. Physics is blind to the fact that its enterprise depends on the very thing it cannot describe. The observer is assumed but unexplained. The knower is absent from the known. The universe fully mapped still leaves out the one who maps it, the unprovability of universal symmetries. Symmetries guide the formulation of physical laws. They explain conservation, simplify equations, and structure theories. Lorentz invariance, gauge symmetry, CPT symmetry, these are pillars of modern physics. But their universality is unprovable. We test symmetry locally, within the limits of our instruments. We assume it holds everywhere, but we cannot verify invariance across the full expanse of the universe, or at all energy scales, or in all hidden sectors of matter. The symmetry may break, bend, or vary without our knowing. Moreover, some symmetries are approximate. CP violation in weak interactions proves that symmetry can fracture under specific conditions. Other symmetries may be emergent, not fundamental, arising from deeper broken realities. Even in theory, perfect symmetry often leads to paradox. Spontaneous symmetry breaking creates diversity. Unbroken symmetry produces featureless sameness. The universe has structure precisely because symmetry fails. Universal symmetry is thus an assumption of elegance, not a fact of nature. It shapes the form of our laws but may not shape the universe itself. We believe in it because it works here, not because it is true everywhere. The collapse of metric space at the Big Bang. General relativity defines spacetime through a metric, a mathematical structure that assigns distance, angle, and curvature. This metric enables motion, causality, and structure. But at the Big Bang, the metric collapses. It becomes singular, undefined, broken. This is not merely a high-energy state, it is the death of geometry. Time and space cease to have meaning. The manifold tears. The coordinates dissolve. There is no point to describe, no distance to measure. The framework of physics loses its foundation. Quantum gravity attempts to regularize the singularity, but often by discarding the metric itself. In loop quantum gravity, the continuum breaks into discrete units. In string theory, spacetime may be emergent. In all approaches, the classical picture fails. This collapse is not an isolated glitch. It marks the origin of everything we observe. And yet it resists inclusion in the very theory that models the universe. The first moment is both essential and inaccessible. Metric space, once the map of all being, has no coordinates at its own birth. The Big Bang's not beginning of time, it is a boundary of description, the conceptual breakdown of infinity in reality. Infinity is a mathematical abstraction, a limit, a direction, a tool. But when imported into physical theory, it collapses into paradox. Infinite mass, energy, density, these are not quantities, they are symptoms of failure. Infinities appear in singularities, in field theory, divergences, in cosmological horizons. But no experiment measures an infinite value. No device detects an unbounded quantity. Reality is finite, measurable. Bounded. The infinite is a placeholder for ignorance. Some physicists argue that true infinities cannot exist in nature. They signal where a theory breaks down, where assumptions lose coherence. Others propose regularization techniques, cutoffs, or renormalization, mathematical sleights of hand to erase the problem. But the deeper issue is epistemological. Infinity cannot be completed. It cannot be fully described. Any system containing it cannot be fully known. The infinite lies beyond comprehension, yet within our models. It contaminates precision with abstraction. Infinity is not a property of the universe, it is a projection of mathematics. And that projection breaks when aimed at the real, the ghosts of higher dimensions. Theories beyond the standard model often require extra spatial dimensions. String theory, M theory, and brain-world models posit 10, 11 or more dimensions curled up at Planckian scales. These dimensions shape particle properties, force strengths, and the constants of nature. But they are undetectable. Their presence is inferred from theoretical consistency, not observation. Their shapes, Calabi-Yau manifolds, warped geometries, are chosen to fit known physics, not derived from it. Every observable feature can be explained by multiple compactification schemes. This leads to an explosion of possibilities. The landscape of string theory contains perhaps 10 to the 500 power, 10 to the 500 power 10, 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 to the 500 power 10 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 to the 500 power. The higher dimensions are ghosts. They determine everything, yet remain forever hidden. Attempts to probe them through collider signatures, gravitational deviations, or cosmological imprints have yielded nothing. The dimensions are real only within the model. Their existence is possible, their necessity unprovable, their influence speculative. The ghosts of higher dimensions haunt the equations but not the world. The circularity of time travel logics. Time travel introduces loops, causal circles that defy linear explanation. A future event causes a past event, which in turn causes the future. Information appears without origin. Objects exist without creation. This is the circularity of time travel logic, an unresolvable recursion. In general relativity, solutions like Gödel's universe and Tipler cylinders permit closed time-like curves. These are not fantasies, they are legitimate, though exotic, outcomes of the equations. But their logical implications are catastrophic. A person kills their ancestor. A message writes itself. The causal chain collapses into a tautology. Quantum mechanics offers no refuge. The many worlds interpretation suggests divergence instead of contradiction, but this multiplies realities rather than resolving coherence. Consistency conditions attempt to enforce self-contained loops, but they do so by fiat, not law. The paradoxes cannot be escaped. They are built into the premise. Any system allowing backward influence dismantles the principle of causality. Time ceases to be an axis. It becomes a web of recursive dependencies. The laws permit time loops in form, but not in meaning. They describe the curve, not the consequence. And in that gap, logic fails. The misalignment of macroscopic and quantum worlds. The quantum world is governed by superposition, uncertainty, and entanglement. The macroscopic world is governed by definiteness, determinism, and separability. Between them lies a chasm. They use the same mathematics but describe different realities. Why don't large objects exhibit quantum behavior? Why do wave functions collapse rather than grow into complexity? Decoherence theory attempts to explain the transition, showing how environmental entanglement destroys interference patterns. But it does not explain outcome. It does not explain why one world appears and not another. The measurement problem remains. The quantum world has no observer. The macroscopic world requires one. The collapse is neither explained nor observed. It is assumed. This misalignment is structural. The equations do not change. The interpretation does. The universe seems to obey different rules at different scales, with no clear boundary between them. A cat is alive or dead, but never both. Until we look. The unity of physics collapses here. One framework, two worlds. No bridge. The phantom mass of gravitational lensing. Light bends around mass. This is a prediction of general relativity, confirmed by gravitational lensing. But in many cases, the lensing effect exceeds what can be explained by visible matter. Galaxies bend light as if they contain more mass, phantom mass, than observations allow. Dark matter is invoked to account for this discrepancy. But the problem remains conceptual. We observe curvature, not mass. We infer presence from distortion. The bending becomes a proxy for the unseen. This proxy rests on assumptions: that light travels in straight lines in flat space, that mass curves space consistently, that there are no hidden influences. If any of these fail, the inferred mass becomes unreliable. Alternative theories of gravity attempt to explain lensing without dark matter, but often introduce other inconsistencies. The phantom mass remains, not detected, only deduced. A shadow shaped by light, not by interaction. Gravitational lensing shows us where the model breaks. It reveals not what exists, but what must exist to preserve the theory. The phantom is real, only because we need it to be. The collapse of predictive power in turbulence. Turbulence is everywhere, in air, in water, in plasma, in blood. It is governed by the Navier-Stokes equations, classical, deterministic, and well-defined. Yet turbulence defies prediction. No closed-form solution exists. Patterns emerge, evolve, and dissolve in apparent randomness. This unpredictability is not due to chaos alone. It is due to the transfer of energy across scales, the cascade from large to small, from ordered to disordered motion. Tiny perturbations grow exponentially, creating eddies within eddies, fractal in complexity. Simulations can model turbulence, but only approximately. They require assumptions, cutoffs, and averaging. Exact solutions remain out of reach. The equations are known. The behavior is not. The Clay Mathematics Institute offers a $1 million prize for proof of the existence and smoothness of solutions to Navier-Stokes in 3 dimensions. The problem remains unsolved. Turbulence is the most common unsolved problem in classical physics. It reminds us that known laws do not guarantee knowledge, that determinism is not prediction, that some systems, though finite, are forever opaque. The limits of time resolution in measurement. Every measurement takes time. The shorter the interval, the less precise the result. In quantum mechanics, the energy-time uncertainty principle forbids infinite resolution. In relativity, simultaneity is frame-dependent. In practical terms, clocks have limits, based on mass, stability, and interaction. But more fundamentally, at the Planck time, on 10 to the power of negative 43 seconds, time itself becomes undefined. Quantum fluctuations of spacetime erase the meaning of simultaneity. Below this threshold, no event can be reliably distinguished from another. Time loses resolution. This creates a boundary in observation. We can model systems, but not probe them beyond the temporal grain of the universe. The present becomes blurry. The sequence of events dissolves. The continuum breaks. No theory fully describes how time arises from quantum processes. We assume time flows, but measure it in discrete steps. Our best instruments approach the edge, but never cross it. The universe ticks, but not smoothly, and the tick itself may be unknowable. The divergence of zero-point energy. In quantum mechanics, every harmonic oscillator possesses zero-point energy, the irreducible minimum energy it retains even in its ground state. This is not a flaw. It is a necessity, arising from the uncertainty principle. It ensures that systems never reach absolute stillness. But when applied to fields, this zero-point energy accumulates. Every mode of every quantum field contributes a finite amount, and there are an infinite number of modes. The total energy of empty space becomes infinite. Even after renormalization, the discrepancy between predicted vacuum energy and observed cosmological constant is catastrophic, by as much as 10 to the 120 to the 120 times 10 to the 120. This divergence is not just mathematical. It undermines the integrity of quantum field theory. It forces the introduction of arbitrary subtractions. It renders energy a relative quantity, defined by what is removed, not by what exists. Yet zero-point energy has real consequences. The Casimir effect, van der Waals forces, quantum fluctuations in inflationary cosmology. It cannot be ignored, but its total contribution defies reconciliation with gravity, with observation, and with itself. Energy, in its most fundamental form, becomes unbounded, And that infinity reveals a gap not in the theory, but in what we think the vacuum is, the erasure of cause in quantum delayed choice. In the delayed choice experiment, a quantum particle, such as a photon, is sent through a double-slit apparatus. The decision to observe which path it takes is made after it has passed the slits, and yet the results change. If which path information is obtained, the interference pattern vanishes. This implies retroactive alteration. A future measurement affects a past state. The photon behaves as if it knew what the experimenter would choose. But there is no signal, no violation of relativity, just a collapse in causal expectation. In quantum eraser variations, the which path information is erased after detection, and the interference re-emerges. The entire sequence of events seems contingent not on past conditions, but on future decisions. This erases cause as we know it. Events are not chained in time. They are correlated by entanglement, not driven by antecedents. The measurement does not reveal a pre-existing state. It defines it. The delayed choice setup does not create paradoxes. It preserves internal consistency. But it annihilates classical logic. The universe does not evolve. It coalesces upon inquiry. And cause, once a pillar of reality, dissolves into contextuality, the semantic ambiguity of energy. Energy is one of physics' most central concepts. It quantifies motion, heat, mass, radiation. It is conserved, transformed, and measured. Yet its definition is context-dependent, abstract, and elusive. In classical mechanics, energy is kinetic plus potential. In thermodynamics, it becomes internal, free, or enthalpic, each with different meanings. In relativity, mass is energy. In quantum mechanics, energy is the eigenvalue of a Hamiltonian operator, and in field theory, it's derived from symmetries of the action. Each definition is precise within its domain and incompatible with the others. There is no unified ontology of energy, no singular account of what energy is. It is a bookkeeping device, a conserved number, a placeholder for change. Energy is not a substance. It is not a force. It has no form, no location, no direct visibility. It is inferred from interaction, conserved across transformation, and yet remains metaphysically undefined. Physics speaks of energy with precision, but its meaning shifts with the lens. The most measured quantity in science may also be its most semantic, the falsifiability crisis in fundamental physics. Science advances by testing ideas. A theory must be falsifiable, capable of being proven wrong by observation. This principle, rooted in Popperian epistemology, has guided physics for centuries. But modern theoretical physics increasingly produces models that cannot be falsified. String theory posits a multiverse of possibilities, each with different laws, constants, and structures. No single prediction emerges. Supersymmetry, once expected at the TeV scale, has been pushed upward indefinitely. Theories of inflation offer flexibility in parameters, postdictions rather than predictions. This drift erodes the empirical anchor of science. Models are judged by internal elegance, mathematical consistency, or anthropic reasoning. Experimental constraints become narrative guidelines, not boundaries. The crisis is not technological, it is philosophical. When a theory explains everything, it explains nothing. When predictions cannot be tested, science merges with speculation. Falsifiability was a boundary between science and ideology. In fundamental physics, that boundary now blurs. The infinite degrees of freedom in fields. Quantum fields are defined at every point in space. Each point carries independent degrees of freedom. Oscillations, amplitudes, fluctuations. This means that even a finite region of space contains an infinite number of variables. This leads to infinities in energy, entropy, and interaction. It requires renormalization, regularization, and theoretical constraints. But the deeper issue is ontological. Can physical reality sustain infinite structure? In practice, detectors measure finite modes. Computations involve cutoffs, but the theory demands infinite resolution. This is not a mathematical quirk. It is a foundational assumption. The concept of a field as continuous, infinitely defined, contradicts the finiteness of measurement, computation, and information. The holographic principle suggests the universe's true degrees of freedom may scale with area, not volume. challenging the very idea of field locality. Fields are the language of physics, but their infinite nature may be fiction, necessary for calculation, fatal for truth. The impossibility of quantum gravity experiments. Quantum gravity seeks to unify the continuous geometry of general relativity with the discrete probabilistic structure of quantum mechanics. It is the most profound theoretical ambition in physics. Yet the energy scales at which quantum gravitational effects become significant, near the Planck scale, are unreachable by any current or conceivable experiment. No collider, no detector, no probe can reach 119.19 to the power of 1919 giga-electron volts. Black holes small enough to display quantum behavior cannot be created. Gravitons, the hypothetical quanta of gravity, are so weakly interacting that they evade all detection. This creates a methodological void. Quantum gravity may exist, but we may never see it. We theorize without the possibility of verification. We model a realm closed to observation, simulating shadows without substance. This is not a failure of technique. It is a boundary of physics itself, a regime that theory demands, but experiment denies. The impossibility is not temporary. It is structural. In this blind zone, every proposal remains speculative. No evidence can choose between strings and loops, emergent gravity or holography. The theory we need may be unknowable, not because it is wrong, but because it is invisible. The disintegration of conservation laws in curved space. In flat spacetime, Noether's theorem guarantees conservation of energy, momentum, angular momentum, each tied to a symmetry. But in curved spacetime, those symmetries dissolve. The geometry is dynamic. There is no global time, no universal frame. This breaks the link. Energy conservation becomes ambiguous. Momentum drifts. Gravity, itself a manifestation of curvature, distorts the very quantities we seek to preserve. In general relativity, local conservation holds through the stress-energy tensor, but global conservation is lost. In an expanding universe, photons redshift, losing energy. Where does that energy go? Nowhere. It simply ceases to exist. The framework does not require explanation. The principle is no longer absolute. This disintegration is not a flaw in general relativity. It is a signal that the principles we hold as sacred are context-bound. Conservation is not universal, it is conditional. And in the very structure of spacetime, that condition fails. We describe a universe where energy is fundamental, but only in the parts that are flat enough to agree. The thermodynamic ambiguity of black holes. Black holes radiate. They have temperature, entropy, and obey analogues of thermodynamic laws. This was Hawking's discovery, and it unified gravity, quantum mechanics, and thermodynamics in a single object. But the analogy strains. The entropy of a black hole is proportional to its surface area, not its volume. Its temperature is inversely proportional to its mass. Its evaporation implies information loss, in violation of unitarity. And yet no microscopic theory fully explains its entropy. Is black hole entropy a count of microstates? If so, what are the degrees of freedom? Are they inside the horizon, on it, or encoded holographically? Each theory offers a different answer, none confirmed. Moreover, the second law, entropy increase, must be redefined to include horizon area. But this is geometric, not statistical. It implies that thermodynamics, the science of probabilities, is geometry in disguise, or that geometry itself is a thermodynamic phenomenon. This ambiguity is not a matter of interpretation, it is a fracture in foundation. Black holes blend laws that elsewhere stand apart. The blend is beautiful, but inconsistent. Entropy was meant to measure ignorance, now it measures surface, and the meaning has not been reconciled. The collapse of predictive symmetry in expansion. Cosmology begins with symmetry, isotropy, homogeneity, uniformity. These are the principles that make the universe understandable. But expansion breaks them. It introduces gradients, anisotropies, and structures. Inflation theory restores early symmetry by positing a period of exponential growth. But that growth itself breaks the very conditions it relies upon. Quantum fluctuations stretched by inflation seed the universe's asymmetries. Order is born from symmetry, but only by violating it. This collapse is predictive in form but retrospective in function. We match the large-scale structure to inflationary models, but those models are flexible, adjustable, reinterpretable. The symmetry exists only in the assumptions. The outcome is always messy. In the late universe, dark energy introduces further asymmetry. Structures dissolve. Horizons isolate. Expansion becomes not a smooth flow, but a rupture of coherence. Symmetry once promised predictability, but in the expanding universe it is a memory, not a principle. The laws still obey it, but the universe does not. The conceptual disunity of force carriers. In quantum field theory, forces are mediated by particles. Photons for electromagnetism, gluons for the strong force, buoyancy bosons for the weak force. Each has mass, spin, interaction rules. Each arises from a gauge symmetry. But gravity is different. Its carrier, the graviton, is hypothetical, undetected, and incompatible with quantum field formalism. It does not fit the symmetry structure. It warps the space-time in which other carriers operate. It is not a particle within space, but a deformation of space itself. This breaks the unity. The standard model's interactions fit within a quantum gauge framework. Gravity defies inclusion. Every attempt to merge them, through strings, loops, or emergent geometry, requires redefining what a force is. Moreover, the forces themselves differ wildly in strength, range, and behaviour. There is no symmetry to unify them without arbitrary scaling. Grand unified theories propose mergers at high energy, but at low energy, the carriers remain strangers. The disunity is not just mathematical, it is conceptual. We describe all forces as particles, except the one that defines the shape of space. The theory unifies matter. Reality does not. The discontinuity of event horizons. An event horizon marks the point of no return. Beyond it, nothing escapes, not even light. It is not a surface, but a boundary in spacetime, defined by causal structure. Yet this boundary creates a discontinuity that fractures the coherence of physical law. To an outside observer, infalling matter appears to freeze at the horizon, never crossing it. To the infaller, nothing unusual occurs at the horizon itself. The same event is described in two irreconcilable ways. No signal reconciles them. No shared description unites the views. This contradiction becomes critical in quantum theory. If information cannot escape the horizon, it is lost. If it is stored on the horizon, where is the mechanism? If it is preserved via holography, the observer's experience becomes a projection. Reality splits by frame. The horizon, smooth in relativity, becomes a firewall in some quantum models, an energetic barrier that incinerates matter. Yet such firewalls violate other principles, like equivalence. The choice is between continuity and information, between smoothness and consistency. The event horizon is not a line, it is a fracture in ontology, a place where perspectives clash, and the laws agree to disagree. The context dependence of observables. In classical physics, observables are objective. A particle's position, a field's strength, a body's momentum, each exists independently of how or whether it is measured. But in quantum mechanics, observables are contextual. Their values depend on the experimental arrangement. This is not epistemic ambiguity, it is ontological dependence. Measuring one observable excludes knowledge of another. Complementarity replaces simultaneity. The system's properties are not predefined. They emerge through interaction. Even the definition of an observable changes with the system. Operators commute or fail to commute depending on configuration. Entangled systems share observables in non-local ways. There is no underlying truth, only framework-specific outcomes. This context dependence undermines objectivity. Reality becomes relational. Observation is not passive, it is constitutive. The measurement does not reveal. It defines. Physics once sought invariants, quantities that hold across frames, devices and theories. Now it faces a world where even the questions depend on the context in which they're asked. The illusion of continuity in spacetime. We experience space and time as continuous. Motion flows, clocks tick, distance unfolds, but theories of quantum gravity challenge this perception. At the Planck scale, Space and time may be discrete, composed of indivisible units, woven into networks or loops. This discreteness is not visual, it is conceptual. The shortest length, the smallest area, a limit below which geometry ceases to be meaningful. Continuity becomes an illusion, sustained by averaging over microscopic granularity. But all physical theories until now assume continuity. Differential equations require smoothness. Fields span unbroken manifolds. Light travels in curves, not jumps. The transition from discrete to continuous remains undefined. The classical world emerges, but the path is obscured. Like a digital image smoothed by filters, space-time seems whole, but is not. Continuity is a convenience of scale, not a property of nature. And when examined closely enough, the seamless world dissolves into fragments. The existential problem of the measurement apparatus. Measurement is the bridge between theory and reality. It turns wave functions into outcomes, probabilities into events. But the measuring apparatus, essential to every experiment, is never part of the theory. Quantum mechanics models systems, not observers. The device is assumed classical. It records outcomes without being described. This creates a structural duality. Quantum systems evolve probabilistically, while the apparatus operates deterministically. But where is the boundary? At what point does the quantum become classical? Is the device truly external, or is its behavior part of the quantum process? No consistent answer exists. This gap is not just theoretical, it is existential. The act of measurement central to physics lies outside its scope. The device that confirms the theory is not modelled by it. The observer is absent from the equation. The universe is measured into being. But the thing that measures is left undefined. It exists in every experiment, but not in the theory that explains them. The incomputability of the universe itself. We imagine the universe as a computable structure, an unfolding sequence of events, governed by laws describable by algorithms. But computation has limits. Some problems are undecidable. Some systems are non-computable. Some truths exceed proof. The universe, if it contains systems of sufficient complexity, may itself be incomputable. No algorithm can predict every state. No finite procedure can extract every fact. Even with perfect laws and initial conditions, evolution may require more information than any model can hold. This is not philosophical pessimism, it is a mathematical fact. Gödel's theorems, Turing's halting problem, and Chaitin's incompressibility theorems all point to this boundary. We can simulate aspects of the universe. We can predict within domains. But we cannot compute the whole. The system exceeds its representation. The universe may be lawful, but not fully knowable. Its deepest truths may not be secrets, but silences. Not hidden by complexity, but excluded by principle. The machine cannot model itself, and neither can the cosmos.